What if everything is a projection? Everything you see, everything you touch, even you, yourself. A world cast from information. Imagine the solid, three-dimensional world is not fundamental, only encoded. A 3D universe emerging from a 2D boundary. That is the holographic principle. Information on the edge gives rise to everything within. Not science fiction, an audacious idea from real physics. It says the laws describing our cosmos may live on its boundary, like a hologram that births depth from a flat script of data. We call it the holographic principle. It challenges our intuitions about space, reality, and information. Could existence be a cosmic illusion, a projection from the universe's edge? The stakes are staggering. Black holes and the fate of information, and what it might say about consciousness. It sounds wild, yet rigorous mathematics is pursuing it, and clever experiments are probing it. Let's start at the edge. Black holes. We will start with black holes, which hinted that information about a volume could be painted on its surface. We will look at the faint, ancient light from the Big Bang for possible evidence etched into the sky. We will examine experiments designed to detect a pixelation of space-time. This is not just philosophical musing. It's a scientific quest to understand reality, and a journey showing just how strange our cosmos might be. The goal is not to convince you that you are a hologram, but to open a door to questions that drive modern physics. These ideas stretch our minds and redefine our place in the cosmos. They remind us the universe is not obligated to make sense to everyday experience. So, let us suspend disbelief and step into a world where length, width, depth might be emergent from a flatter reality. Let's explore the science behind the cosmic hologram and ponder what it could mean for us, the inhabitants of this grand projection. Okay. So, our journey into the holographic universe begins in the most extreme environment imaginable, the crushing, inescapable heart of a black hole. For a long time, physicists viewed black holes as simple, voracious cosmic vacuum cleaners. Anything that crossed their boundary, the event horizon, was thought to be lost forever, its information utterly erased from the universe. However, in the 1970s, the work of Jacob Bekenstein and Stephen Hawking turned this picture on its head. They discovered that black holes are not just empty voids. They possess entropy, a physical quantity that measures disorder, and more fundamentally, the amount of information an object can hold. This was a revolution in itself. The truly bizarre discovery was not just that black holes had entropy, but how that entropy was calculated. You would naturally assume that the information capacity of an object, how many bits of data you could pack into it, would depend on its volume. A bigger box should hold more stuff, right? But for a black hole, that is not the case. Bekenstein and Hawking found that a black hole's entropy, its total information content, is proportional not to its three-dimensional volume, but to the two-dimensional surface area of its event horizon. This was a shocking and counterintuitive result that nobody saw coming. Think about what this means. It is as if all the information about every single particle that ever fell into the black hole, every star, every planet, every stray atom, is not lost in the three-dimensional abyss inside, but is somehow encoded on the two-dimensional surface of the event horizon. The event horizon acts like a cosmic hard drive, storing a complete record of everything that has been swallowed. The strange behavior of black holes gave physicists a powerful hint, which was then generalized into a bold conjecture about the entire universe. This is the holographic principle first proposed by Gerard 't Hooft and later refined by Leonard Susskind. In its simplest form, the principle states that the description of a volume of space can be thought of as encoded on a boundary to that region, preferably a light-like boundary like a gravitational horizon. It is named after a regular hologram, the kind you might find on your credit card or in a science museum. A hologram is a flat, two-dimensional piece of film that, when illuminated by a laser, produces a fully three-dimensional image. All the information needed to create the illusion of depth in the holographic image is stored on the two-dimensional surface of the film. The holographic principle suggests that the universe might operate in a similar way. The three-dimensional world we perceive, with all its galaxies, stars, planets, and people, could be a projection of physical processes taking place on a distant, two-dimensional boundary. This does not mean our world is fake, any more than a three-dimensional movie is fake. It means that the fundamental description of reality might be simpler and flatter than it appears, with the richness of our three-dimensional experience emerging from it. This idea gained powerful support from a branch of theoretical physics called string theory. In the late 1990s, physicist Juan Maldacena discovered a stunning mathematical connection known as the ADS-CFT correspondence. While the name is a mouthful, the concept is a beautiful illustration of the holographic principle in action. Maldacena found a precise mathematical duality. A theory of gravity in a specific kind of five-dimensional saddle-shaped universe called anti-de Sitter space, or ADS, was mathematically equivalent to a non-gravitational quantum field theory, a conformal field theory, or CFT, living on its four-dimensional boundary. The two theories looked completely different, yet they described the exact same reality. What makes the ADS-CFT correspondence so compelling is that it provides a concrete, calculable example of holography at work. It shows that a world with gravity and extra dimensions can emerge from a lower dimensional world without gravity. Difficult problems in the gravitational theory can be solved by translating them into easier problems in the boundary theory, and vice versa. While our universe is not an anti-de Sitter space, this correspondence provides a mathematical playground where physicists can prove that the holographic idea is not just a philosophical whim. It is a feature that can arise from the fundamental laws of physics, suggesting that space-time itself might be an emergent phenomenon. If the holographic principle is a true feature of our universe, we should be able to find evidence for it. But where would you even begin to look for signs that our three-dimensional world is a projection? One of the most promising places is the oldest light in the cosmos, the cosmic microwave background, the CMB. The CMB is the faint residual heat left over from the Big Bang, a snapshot of the universe when it was only about 380,000 years old. This ancient light fills the entire sky, and while it is remarkably uniform, it contains tiny temperature fluctuations, subtle hot spots, subtle cold spots. Those fluctuations eventually grew into the galaxies and clusters we see today. These features are not statistically impossible, but they are unlikely enough to make cosmologists wonder if something is missing. This is where the holographic principle re-enters the picture. Some researchers propose that if our universe is a hologram, it might have left a distinct signature on the CMB. In a holographic scenario, early universe physics would be described by a two-dimensional theory, not a three-dimensional one. Calculations based on this idea predict a slightly different pattern of fluctuations compared to standard inflation. When scientists compared a simple holographic model to actual CMB data, they found it fit the observations surprisingly well, in some cases slightly better than standard inflation, especially for some large-scale anomalies. This does not prove the universe is a hologram. The evidence is far from conclusive, and many other explanations exist. The holographic models tested are still rudimentary. Still, the fact a holographic model can reproduce observed data at all is intriguing. The CMB is a vast celestial billboard with the universe's earliest secrets written on it, studying its patterns with increasing precision. While cosmologists look for clues in the vastness of the sky, other physicists have been searching for evidence of holography at the smallest scales imaginable. If our three-dimensional universe is a projection from a two-dimensional surface, then spacetime might not be smooth and continuous. Instead, it could be pixelated, made of fundamental, indivisible units of information, like the image on your computer screen made of pixels. The size of these cosmic pixels would be incredibly tiny, the Planck length about 1/trillionth of a trillionth of the diameter of a hydrogen atom. Detecting such granularity is an immense technological challenge. To hunt for holographic noise, scientists at Fermilab built the Holometer. It was designed to test whether spacetime has a fundamental jitteriness at the Planck scale. The Holometer uses a pair of powerful laser interferometers devices that split a beam of light, send the two halves down different paths, and then recombine them. If the paths are exactly the same length, the light waves recombine perfectly. If one path fluctuates even infinitesimally, it disrupts the interference pattern. The core idea: if spacetime is pixelated, reality should be constantly jittering at the Planck scale. That jitter would make the mirrors in the interferometers fluctuate randomly and subtly. That would create a distinctive noise signal in the recombined laser light. The holometer was engineered with exquisite sensitivity, theoretically capable of detecting a sideways jitter as small as the Planck length. It was a direct physical test of the idea that our three-dimensional space emerges from finite two-dimensional bits of information. After years of data collection and analysis, the holometer announced its results. It found no evidence of the predicted holographic noise. The experiment showed spacetime is smooth and stable down to the scales it could measure, ruling out some of the simpler holographic models. But this null result does not kill the holographic principle entirely. It places constraints on what kind of holographic universe we might live in. More complex models predict noise the holometer was not designed to detect. The experiment was a bold attempt to touch the graininess of reality, and its results guide physicists toward more refined theories. As physicists delve deeper into the holographic principle, they are uncovering a profound connection to one of the strangest features of the quantum world: entanglement. Quantum entanglement is the spooky action at a distance that so troubled Albert Einstein. Two or more particles become linked, their fates intertwined no matter how far apart. If you measure one entangled particle, you instantly know the property of the other, even on the other side of the galaxy. This seems to defy the cosmic speed limit of light. Entanglement used to seem niche. Now many physicists think it might stitch spacetime together. In the context of ADS-CFT correspondence, researchers found a formula connecting boundary entanglement to the geometry of the interior gravitational space. The idea is summarized by ER equals EPR wormholes, Einstein-Rosen bridges, ER entangled particles, Einstein-Podolsky-Rosen pairs, EPR. The geometry of spacetime manifests quantum entanglement patterns on the boundary. Space is not fundamental. Space is emergent from a network of quantum entanglement. Think of it like a quilt. From a distance, a smooth, continuous fabric. Look closely. It is made of individual threads, entangled qubits woven in an intricate pattern. The connection pattern determines the shape and curvature of the quilt. The entanglement pattern could create geometry, curvature, even the dimensions of our universe. This offers a possible path to unify gravity and quantum mechanics. If spacetime is built from quantum information, qubits linked by entanglement, then gravity might not be a fundamental force, but an emergent, thermodynamic-like effect, arising from collective behavior of quantum bits. This strengthens the holographic idea by giving a physical mechanism how a lower dimensional information system could produce our rich geometric world. The secret to spacetime may be hidden in the spooky connections of the quantum realm. When people first hear about the holographic principle, they often confuse it with another mind-bending idea: the simulation hypothesis. The simulation hypothesis proposes that our entire universe and everything in it is a sophisticated computer simulation created by a more advanced civilization. In this scenario, we are like characters in an incredibly advanced version of The Sims, and the laws of physics are simply the lines of code that govern our reality. While both ideas challenge our sense of what is real, they are fundamentally different in their scientific and philosophical implications. The holographic principle is a statement about the laws of nature, while the simulation hypothesis is a statement about our universe's origin. The holographic principle arises from within physics, specifically from the study of black hole thermodynamics and string theory. It does not posit an external creator or a programmer. Instead, it suggests that the mathematical framework needed to describe our universe might be fundamentally information-based and lower-dimensional. It is a claim about how nature itself organizes and stores information. If the principle is correct, it is not because someone is running a simulation of us. It is because the universe just is that way. The laws of physics themselves have this holographic property, regardless of how the universe came to be. In contrast, the simulation hypothesis is a much more speculative, top-down idea. It presumes the existence of a base reality outside our own, inhabited by the simulators who built and run our universe. It implies intent, purpose, and an intelligence behind our existence. While some philosophers and physicists have proposed ways we might look for evidence of a simulation, such as searching for glitches in the matrix, or discovering that the laws of physics are optimized in a way that suggests computational shortcuts, it remains largely in the realm of philosophical speculation. The holographic principle, on the other hand, makes testable predictions, such as the Bekenstein-Hawking entropy formula and the potential for holographic noise. It is helpful to think of the distinction this way. The holographic principle is like discovering that a book can be fully described by the digital data in a .txt file. The information is the same, just stored in a different format. The simulation hypothesis is like discovering that the book was written by an author for a specific purpose. One is a statement about the structure of information. The other is a statement about its origin and intent. While both ideas radically alter our cosmic perspective, only the holographic principle is currently a driving force in mainstream theoretical physics, offering a concrete path toward unifying gravity and the quantum world. So, let us say the physicists are right. Let us imagine for a moment we are living in a hologram. What would that change about daily life? If you stub your toe on a table, would the pain be any less real? Would a beautiful sunset be any less breathtaking? Most physicists say, no. Our experiences, emotions, thoughts, choices remain real and meaningful. Realness comes from interactions, not metaphysical foundations. Think of a character in a novel. To them, the story world is completely real. They fall in love, they face challenges, they make decisions with consequences. Their world is printed words, yet their existence has significance. If our 3D world is a projection of 2D information, it is still the arena we live in. Physics, chemistry, biology. Those laws still operate consistently inside the projection. The holographic principle prompts questions about free will. If all information is encoded on a boundary, is the future already written? Not necessarily. The holographic screen's information could evolve under quantum laws. Quantum laws are probabilistic. There can be genuine randomness. There can be unpredictability. The principle tells us how information is stored, not what it must contain. The free will versus determinism debate remains unresolved philosophically. The holographic principle impacts our scientific view, not our felt experience. Knowing Earth orbits the Sun does not change feeling a sunrise. It changes our cosmic perspective. Likewise, a holographic universe would not make love or sorrow less potent. It would give a deeper, more wondrous understanding of the stage we live on. The holographic principle stands today as one of the most provocative and promising ideas in modern physics. But it is far from a settled fact. It is an unfinished map, with vast territories still unexplored. The search for definitive proof continues on multiple fronts, pushing both our theoretical understanding and our experimental capabilities to their limits. One of the biggest challenges is bridging the gap between the idealized mathematical models, where holography works perfectly, like the ADS-CFT correspondence, and the messy, complicated reality of our own universe, which is expanding and has a different geometry. Physicists are working tirelessly to develop a holographic description that applies to a cosmos like ours. On the experimental side, the quest is just as active. While the Fermilab holometer set important limits, the search for space-time graininess is not over. New experiments and new technologies, perhaps leveraging quantum sensors or astronomical observations, could one day be sensitive enough to detect the subtle effects of a pixelated reality. Furthermore, our observations of the cosmos continue to improve. Future surveys of the cosmic microwave background and the large-scale structure of galaxies will provide ever more precise data, allowing us to scrutinize the universe's initial conditions for any telltale holographic signatures. The information paradox of black holes also remains a key theoretical laboratory for testing these ideas. Even if the holographic principle, in its current form, turns out to be incorrect or only part of a larger story, its influence has already been immense. It has forged powerful links between previously disparate fields of physics, connecting gravity, quantum mechanics, and information theory in profound new ways. It has taught us to think of information not just as something we use, but as a fundamental building block of the universe itself. The questions it raises have forced us to confront the very nature of space and time, pushing us toward a deeper and more unified description of reality. So, as you look up at the star-filled night sky, consider the possibility. Are you looking out into a vast, three-dimensional space? Or are you an actor within a grand cosmic projection, gazing at an image whose information is stored on the boundary of your universe? We do not yet know the answer, but the pursuit of that answer is what science is all about. It is a journey driven by curiosity, guided by mathematics, and tested by observation.